Hello, my name is Will Sewell,
I'm Colin Brace.
And I'm Jeremy Hayes.
and this is our energy comparison project.
For our criteria selection, we chose cost, sustainability, efficiency, scale, human impacts, safety, and social structures.
Our first criteria is cost. Cost will be defined by two quotients. Initial cost will be factored in by taking the startup cost over the capacity of the power plant. Operational cost, on the other hand, will be measured by comparing yearly energy output and maintenance costs.
We define sustainability as the responsible use of resources and the preservation of the environment to meet present needs without compromising our future. For energy, this means ethically acquiring the resources to manufacture the technology and the sourcing of its fuel. Within sustainability, there's a level of attention paid to the impacts on different social groups, but we will cover these in another criteria. Sustainability is literally defined as the quality of being able to continue over a period of time. However, this lacks an assurance of the quality of this continuance. Our energy technologies will be ranked according to their total emissions and pollution, their longevity, and their waste.
Our next criteria is efficiency. Efficiency is an important metric for evaluating how well energy is transferred from one form to another. For multiple energy sources, the efficiencies will be different and represent different things. In this case, the efficiency will represent the ratio of the electrical output to the energy input, which will vary depending on type of source. For example, with solar, it will be the sunlight. For hydro, it'll be the potential energy in the water. And for nuclear, it will be the thermal energy produced by the nuclear fission reaction.
Scale will represent how well an energy technology can be ramped up or down to meet a client's needs. It includes the cost to scale the technology up or down and whether it is a linear trend or not. We will compare it to the added energy to understand the implications of a smaller or larger system.
Our next criteria is human impacts. Human impacts relate to the effects that a given energy source has on the humans operating and living near the power plant. Many things such as air quality, fuel hazard, and industrial fallout are considered impacts from a plant that are continuous and side effects of normal operation. These effects are usually unnoticeable in day-to-day operation, but present credible threats to the public over years or decades of exposure. To pass this criteria, proximity to or operation of a plant must be safe over decades of exposure.
The next criteria is social structures. Social structures will represent the necessary regulatory bodies and societal security to use this form of energy. This criteria will address how some forms of energy production require more regulation to be safe and ensure the security of the people within a society. Can this technology be implemented in a less advanced society? What are the necessary regulatory bodies for the safe operation of this form of energy? Does the society have the resources to address and respond to an emergency? These are the questions that we will ask and evaluate in the coming slides.
The last criteria we're going to look at is safety. Safety relates to the damage potential of an energy system to the human population nearby and the credibility of this danger. Both the maximum potential destruction and the possibility of this occurring are considered. To pass this criteria, one of the two aspects considered must be virtually zero. For example, either the worst case scenario must be relatively tame, or the possibility of this scenario is impossible.
The first energy production method that we will be evaluating is nuclear energy. Nuclear energy is energy that's released from reactions that occur within an atom's nucleus. There are two main types of nuclear reactions: nuclear fusion and nuclear fission. Nuclear fusion is what happens in our sun, and it's when small nuclei fuse together and release immense amounts of energy. So far, we have not figured out how to harness this on Earth. Nuclear fission is when you break apart large nuclei into smaller ones, creating more stable elements. And this releases a ton of energy as well. This is how nuclear bombs were created, or also with nuclear power plants throughout the world. The energy is produced by nuclear reactors from the difference in mass between the products and reactants of the nuclear reaction. The energy is produced is equal to E equals mc squared. 20% of U.S. energy is from nuclear. This next slide is about the evolution of technology for nuclear energy being used for electricity production. The first type of nuclear reactors were actually created for naval submarines to propel them through the water. This is because when you're underwater, you cannot burn traditional fuel, and that's why nuclear energy was the best candidate for a submarine. The Gen 1 reactor was an experimental breeder reactor that was designed and operated by Argonne National Laboratory. After this, Eisenhower proposed his Atoms for Peace program, and this is when we started using nuclear energy for submarines, and the Mark I was a naval prototype reactor that was put in submarines. It was a pressurized water reactor, or PWR, which I will get to further in this presentation. Generation 2 reactors were the first ones that connected to the grid and were used for commercial operation. The first Generation 2 reactor was a Westinghouse reactor called Yankee Roe. It started in 1960 and shut down after 32 years in 1992. Diablo Canyon is also a later Generation 2 pressurized water reactor. In the U.S., there are boiling water reactors and pressurized water reactors. Generation 3 reactors are ones that were created in the early 2000s and designed in the early 2000s and late 1990s. They're like Gen 2, but they have advanced design improvements and employ some technology to make them more automated and redundant in the case that there's an emergency. They address many of Gen 2's vulnerabilities and decrease the likelihood of nuclear accidents. Gen 3 Plus are further improved safety and resilience through the application of modern controls, design, and technology. The development of small modular reactors also falls under Gen 3 Plus. Generation 4 reactors are the new reactors that are being designed right now, and they use other coolants than water, so you can produce power with at lower pressures and achieve better safety and higher efficiencies. This will be the last slide before we go over the criteria. This gives an overview of the current U.S. nuclear energy industry. Below is a reactor that is actually very close to us in San Luis Obispo, about 15 miles away on the coast. It's Diablo Canyon reactors 1 and 2, and they are the last operating nuclear reactors in California. They are typical Generation 2 pressurized water reactors, and their construction began in 1968 and finished in 1985. They have been running since then and producing up to 13% of the state's power. This is about 2,000 megawatts. The most recent reactors that were built in the U.S. are Vogtle 3 and 4. They are Generation 3 Plus reactors, and this is the type of reactor that I will be evaluating today through the criteria. They began the construction in 2013 and just finished 10 years later in July 31st of 2023. The first criteria that I'm going to evaluate is cost for nuclear energy. Nuclear energy has a relatively high installation cost, but a low operating cost. The installation cost, or capital cost, are about $6,041 per kilowatt electric, which is as of 2020. There's also long construction periods, which lead to no return on investment until about 10 to 13 years after the initial construction begins. However, the operational costs are relatively small, and it can produce tons of power, so it creates about a $29.13 per megawatt hour as an operational cost, which is actually really low. Decommissioning costs are also very significant at about 9 to 15% of the initial capital cost. When you're talking capital cost in the multiple tens of billions of dollars, this is a very significant number. Also, due to the lack of interest in the nuclear industry over the past 30 years, a lot of the industry that produces parts and are certified to produce parts for nuclear plants has disappeared because there's just no money in it. And this has also increased installation cost immensely. If we were to reinvest in nuclear and more plants were to be built, a lot of this industry would reemerge and potentially significantly lower the cost of nuclear power. The first criteria that we're going to evaluate for nuclear energy is sustainability. Nuclear energy requires the least amount of land to generate electricity for the grid. Only 1.3 square miles are required to generate enough electricity for almost 750,000 homes. This is assuming that you have one reactor that has a power capacity of about 1,000 megawatts electric. However, there are large cooling water requirements for a nuclear reactor. Oftentimes, they're placed next to the ocean or a large lake in order to meet these requirements. Another option is cooling towers, where they allow the water to somewhat evaporate to cool the remaining water. There are zero carbon emissions from nuclear energy, and they work in places where solar, wind, and hydro don't typically work. Uranium fuel is limited. However, there is potential to run reactors with thorium or plutonium or depleted uranium. Nuclear does also create waste that isn't recycled in the U.S. and doesn't have a good permanent storage solution. So that is another thing to consider for sustainability. The next criteria that we're going to evaluate for nuclear energy is efficiency. The AP1000 reactor, which is the Generation 3 Plus reactors that were just put online in the US and Georgia, have about a 32.5 thermal efficiency, and they employ a standard Rankine cycle. However, the newer reactors use fuel more efficiently, leading to less waste. So they do have a relatively low thermal efficiency, about the one you'd see with any heat power plant that has a Rankine cycle. But with nuclear energy, it's slightly less of a concern because the fuel is so energy dense, and you get a lot of thermal energy from such little amounts of uranium anyways. The next criteria for nuclear energy is scale. Nuclear power plants are very big, and a large population is required to build a reactor. This is because the power of nuclear reactors are typically 1,000 megawatts electric per reactor. This is enough power for millions of people. This makes nuclear energy an impractical solution for smaller communities. Companies like NuScale are trying to change that with the development of small modular reactors that are more within the range of 50 megawatts electric. Nuclear energy is also not a variable form of electricity. Yet once you start a reactor, it stays at 100%. You can't change it with the fluctuations in demand on a grid. The next slide is nuclear energy's human impacts. The human impacts of nuclear energy are improved air quality when compared to fossil fuel alternatives, and there's no significant radiation that exists outside the reactor's core. Under the worst circumstance, it could displace people and deliver radiation. The safety of nuclear energy is the next criteria we will evaluate. It must be mentioned that there have been catastrophic nuclear accidents in the past, such as Chernobyl and Fukushima. 3 Mile Island was almost a catastrophic reaction, but it lacked the amount of radiation that was output by Chernobyl and Fukushima. Despite these accidents, nuclear energy is actually quite safe. Due to automation of new plants that allows them to shut themselves down in the event of emergency, and new technologies, reactors have become increasingly safe. New small modular reactors can also be passively cooled in the event of emergency, leading to less requirement for zoning areas and potentially to be used in smaller areas. Additionally, assessments of areas for reactors are now more used. This includes if there's any faults in the area and if there's tsunami risk. So Diablo Canyon in SLO might be a little risky because it's on the coast of California where there are many faults, and it also has the potential to be hit by a tsunami. So that's a risk factor that we now evaluate for. All right. The last criteria for nuclear energy is social structures. Nuclear energy requires immense regulation and resources. Only more developed and advanced countries can use nuclear energy. The country needs a commission to regulate it, The security of the fuel and waste are also necessary, and the society needs the ability and resources to respond to a problem. This leads to only countries with immense amount of resources, the ability to regulate regulate a whole industry to be able to use nuclear energy. Its high capital cost also make it less accessible to lower income nations. So this is very important because you don't want nuclear fuel to get into the wrong hands, as it could be used to make weapons of mass destruction. And you also don't want the nuclear waste leaking into areas and contaminating food supplies or giving people radiation. So it's important that you have these agencies and government organizations that can regulate nuclear energy. And therefore, it requires a lot of social structure.
Our next energy technology is solar. Solar uses light from the sun to power a photovoltaic cell to create energy. Solar energy is also the foundation of life, and humanity has relied upon it since our conception. The first PV cell was invented in 1883, but was not economically viable. In 1954, we invented the first silicon PV cell, allowing us to power a small electronic device at 4% efficiency. The PV cell works by using the photovoltaic effect of semiconductors. Some of the photons are absorbed by the electrons, which jump the band gap and then create an electron hole. This electron hole then creates a flow of electrons, creating a current, which is what we use to generate power. There are three main components of solar systems. Every solar system needs a solar panel to house the PV cells and absorb the sun's photons. Then an inverter is used to convert the DC current coming from the panel to an AC current, and then some sort of load on the other end. Other common features include solar tracking arrays, meters to check usage, and battery storage are a few. Next for solar is the cost. In California, the average cost per watt is $2.73 after government incentives. The national average for residential solar systems costs roughly $23,879, but after the 30% investment tax credit, it drops to $16,715 for a 5 kilowatt system. In the US, expect to pay between $2.50 and $5 per watt, depending on state to state. For solar systems today, modeling annual maintenance is difficult due to the different scales, geography, and extenuating circumstances involving solar. However, the NREL, National Renewable Energy Laboratory, suggests that residential solar costs around $30 per kilowatt in annual fees, maintenance fees. To calculate a cost per kilowatt hour, we would take our annual costs and divide it by the total annual output of the system. For example, a 5 kilowatt system in SLO receives an average of roughly 6 peak sun hours during the year, and from that outputs roughly 8,100 kilowatt hours a year, meaning an annual cost of roughly 2 cents per kilowatt hour, a very meager number. Next is sustainability. Of the three energy technologies, solar ranks by far as the most sustainable. The main reason is its fuel is sunlight, which is a near infinite source and has no pollution or emissions related to it. The solar systems, on average, last roughly 20 to 30 years, with some lasting even up to 50 years, a very long lifespan indeed. The main resource used in the PV cell is silicon, which is the second most abundant element on Earth. However, there are some minor disadvantages due to the harmful chemicals used in manufacturing, a loss of habitat due to locating the solar fields, some destructive mining practices used for allocating the resources to build the solar panels, and waste management processes involving the recycling and decommissioning of solar systems. However, these can easily be mitigated through ethical sourcing of resources and improved manufacturing techniques. Overall, solar is by far the most sustainable of the selected technologies due to its lack of pollutants, long lifespan, and resource allocation. Solar efficiency. Efficiency for solar is extremely nuanced due to the unpredictability of the sun. At the NREL, the highest efficiency ever recorded was 47.1% using the controlled light of 143 suns, a hypothetical number, but one interesting for science. However, practical PV cells are limited to roughly 30% efficiency due to the nature of the PV cell and the junction between the semiconductors, with consumer market solar panels coming in around 15 to 22%. Solar insolation is the measured amount of energy, solar energy, that reaches a specific area on a surface in a given amount of time. This plays another large role in calculating the efficiency of a panel due to the geographical location of the panels. Solar efficiency is also greatly impacted by temperature, as some studies show that per degree increase in temperature, output voltage can drop by as much as 2.2 millivolts. Overall, solar is the least efficient of the three energy technologies due to its meager 20% efficiency. Solar safety. In terms of the three energy technologies, solar is the safest by a long shot. The only real concerns with solar is the wiring and harnessing that can lead to fire and electrocution. The panel itself is not very flammable, but the incorrect wiring can lead to issues. There are no emissions, so they pose no health impacts as well. Scale. One of the best advantages of solar is its scalability, as the main thing needed to add more capacity is more PV cells. When adding more panels, more infrastructure is needed due to the added complexity, such as access systems, inverters, and tracking software. Due to the simplicity of the system, solar panels can be used for small electronics like outdoor lightings or as large as 500 plus megawatt solar farms. Because of its flexibility, there is no optimum size, meaning every application will be dependent upon clients' needs. Human impacts. Solar is one of the least impactful technologies on humans due to its small footprint and lack of emissions and pollutants. Besides being in remote locations, there are no major exposure dangers to operators or nearby residents. Solar passes human impacts with flying colors. Social structures required. One of the most important aspects of utilizing solar energy is the legislation and governmental regulations surrounding its adoption. These social structures directly influence whether customers buy more or less of solar. Solar's high installation costs act as a barrier for many, especially lower income peoples. And without incentives from the government, it can be impossible to adopt these sustainable energy technologies, especially for people of lower income classes. For example, California just passed NEM 3.0, an amendment that will reduce payments sent to solar customers that send energy back into the grid, which has actually immediately slowed the number of residents adopting new solar systems. Also, the Inflation Reduction Act, passed by the Biden administration, directly opened billions in funding for solar research, manufacturing, and construction, leading to a recent boom in solar technology. The higher costs of solar result in less access for poorer nations and people, causing inequity with regards to sustainable energy resources.
The last energy system we're going to analyze is hydroelectric power. The first power plants were designed to be powered by rivers back in the mid-17th century. The designs and size for hydroelectric power plants vary extremely because of their dependence on geography. By damming up a river or similar waterway, potential energy is gathered and then deliberately released through a set of turbines to generate power. The average age of a hydroelectric plant in the U.S. is 64 years, making it the oldest power generation process. Cost. Since 2000, hydroelectric projects have accounted for $271 billion in investment to install 113,344 megawatts of capacity. Hydroelectric plants average about $2,380 per kilowatt of capacity, over double the average cost of coal and natural gas plants. Maintenance costs for hydroelectric dams are usually based on the total investment of the dam, with a yearly average of 2 to 4%. Large hydroelectric dams average about 45 kilowatts per year for maintenance. The next criteria is sustainability. Normal operation of a hydroelectric power plant requires no fuel to operate, and so it creates zero air pollution. Hydroelectric dams also enjoy the longest operating service that can stretch over 100 years with proper maintenance. However, damming a river creates environmental concerns and can damage the ecosystem. Nearly all dams have a fish pass system, which can help mitigate environmental damage, but fish populations suffer whenever a dam is created on their native river. Efficiency. Hydroelectric dams are the most efficient power plants in the world. Most plants operate well over 90% efficiency, turning the potential energy in water into hydroelectric power. As a hydroelectric plant is quite simple in the design, the high efficiency is a result of the low energy loss to inlet pipes and the turbine. Scale. Because hydroelectric plants are driven by waterways, their design and size are often driven by demand and, more importantly, the surrounding geography. However, once a river has been dammed, it's relatively inexpensive to add capacity to a plant, just building off existing infrastructure. Hydroelectric plants are also incredible at quickly scaling up and down production to match demand, as they can simply allow more water through the turbines already stored or activate inactive turbines to increase production. Human impacts. Because a hydroelectric plant requires no fuel to combust, it doesn't release any dangerous air or similar pollutants for nearby populations or operators to inhale. It also doesn't release any contaminants into the water or any poisons into local wildlife that may be consumed. For these reasons, hydroelectric dams have no long-term exposure risks and pose no danger to humans in contact over extended periods of time. Social structures. Dams hold back immense amounts of water that, if released improperly, could cause billions in property damage and millions of lives. Dams are often either government or privately owned and must be rigorously maintained and inspected to avoid complications or failures. Large organizations like the California Department of Water Resources or the U.S. Army Corps of Engineers are responsible for operating and preserving these structures against neglect or disaster. The last criteria we're going to discuss is safety. Hydroelectric dams are remarkably safe against partial or total failure. A breach in a large dam system would be catastrophic to all downstream, and the potential for destruction would be guaranteed if this were ever to happen. However, because of the factors of safety in place, as well as the constant upkeep of dam facilities, it renders hydroelectric dams as completely safe power plants.
Reflecting back on our research, we can confidently say that we learned lots about our selection criteria, the selected energy technologies, and the impacts they have on their constituents. For example, the method by which we value our criteria eventually decides which energy technology is considered best by our guidelines, which is a biased method. For example, we place sustainability as the most important criterion. However, someone else, let's say a business person, may put cost or reliability as their first priority, which will lead to differences in the perceived, in quotes, best technology. Another thing to consider is that the geography plays a large role on considering what technology is most applicable. Ethically, we must consider the impact on the Earth and its inhabitants as our main priority, as we have seen from our history that choosing to neglect to do so leads to catastrophic damage and irreversible consequences. Current energy selection practices vary based on jurisdiction. For example, PG&E in California started the Camp Fire, which killed 84, destroyed an entire town, and is only fined $4 million in damages. So for a group like that, cost would be considered their main priority. However, new developments in the solar industry have shown us that there are other more important criteria to suggest, such as sustainability and human impacts.
After some reflection, we have decided a few criteria that we will adjust and change. The first is to de-emphasize efficiency. Despite efficiency being a very important and telling metric, it's a bad metric for comparing the types of energy sources that we have. For nuclear, it's going to be the thermal energy and how well that's converted into electricity. For solar, it's going to be how well that solar radiation is converted into electricity. And for hydro, it's going to be how well the potential energy in the dam is converted into electricity. So because these are such different sources of energy, I feel like efficiency is not a proper metric to compare these energy sources with. We can move this weight into the cost and the sustainability of the actual source. We want to increase the emphasis on safety to better protect the people in the immediate area. We feel that the safety of an energy source is very important, if not the utmost importance of an energy source. So it's something that we don't take lightly and increase the emphasis upon. Also, it's worth noting that geographical factors have an impact on what plant type can be used, like whether or not there's a river there, whether or not there's a lot of sun in the area, and it just has to do with the natural resources available. So we increased the weight on scale, and that would account for that.
After looking at our final results, a couple patterns are clear. Overall, solar comes out on top mostly because it's stellar performance in cost, sustainability, and safety. Nuclear comes in last, mainly because of its immense initial construction cost, middling efficiency, and inability to operate at a small scale. Hydro takes second place due to its exceptional efficiency and safety, but is held back by its scale and sustainability.